Okay, I wanted to give you a couple applications of graphing quadratic equations, and people are in love with gravity. Keeps us on the ground, right? So here's an equation that represents the motion of an object in free fall, meaning just under the influence of gravity. And I think we talk about this a little bit in the factoring section, certainly in the solving quadratic equations section. But I just want to see what the graphs of these look like. And let me explain what this equation says. So first of all, the g here is the gravitational constant near the surface of the Earth. It's like the pull on us from the Earth near the surface of the Earth. It's actually a little bit different if you go really high, like the top of Mount Everest, but very slightly. So g is approximately, there's a couple different ways we like to look at it. It's about 32 feet per second. That is the magnitude, feet per second squared. 32 feet per second squared. That is the magnitude, the strength of the pull of gravity. Technically, it has a negative sign. That's where this negative comes from. Negative by going downward toward the center of the Earth, essentially. Okay, but just the magnitude, just the absolute value is 32 feet per second squared. It's about also 9.8 meters per second squared. And these two are kind of the popular numbers that are used for g. Now what does the v naught mean there? It looks like v0. Some people say it v0. I use naught, v naught. And that's the initial velocity. Of anything that is now in free fall. So if you throw a baseball, it has some initial velocity, after which time it's in free fall under the influence of gravity only. The y naught, in this case, I'm going to call this initial height. Initial height. Guess I could have used h in my equation. You see it written that way often with h equals -1/2 gt squared plus v naught t plus h naught. I don't know, I like x and y. It doesn't really matter. So let's take an example of a potential problem using some of these quantities. Suppose we are, let's go with the meters per second g, and let's also say 9.8 is kind of close to 10. So if I do half of 10, I get 5. So I'm going to say y is equal to -5t squared. Okay, and that's just because of the gravitational constant. Let's say there's 0 initial velocity on whatever it is we're doing, but we're starting 30 meters high. So I don't know, what kind of thing could this represent? I guess it could represent you standing on the top of a 30-meter high building, about 90 feet high building, and dropping something. Okay, it didn't have an initial velocity. If you just let it go, you didn't throw it up, you didn't throw it down with any speed. It's just 0 initial velocity. So really, of course, you'd see the equation written without that 0 term in there. It would look just like this. And let's go ahead and graph it. I would like to see what's going on at t equals 0 seconds. If I were looking for the vertex, remember I could find the vertex. This is a standard form quadratic equation, so I could find the vertex by doing -b over 2a, which also gets me 0. The coefficient, the leading coefficient is negative, so I know it's a sad-faced looking parabola. And the highest point is going to be at t equals 0, as indicated by the vertex. So let me just make a little baby table of t and y. I don't have x and y. I do like using t instead of x for these problems because t stands for time. It makes sense to the situation. So let's see what's going on at 0 and maybe 1 second and 2 seconds, maybe even 3 seconds. We'll just keep going. That seems like a good sample, 4 seconds. So let's see, if I plug in 0, y equals -5 times 0 squared plus 30 is clearly just equal to 30. Plug in 1 squared plus 30 gives me -5 plus 30, where I already did this exponent and multiplication equals 25, all right. Okay, so 1 second after it drops, it went from your initial height of 30 down to 25 meters. All right, how about 2 seconds? Oh, I didn't put an equal sign there. -5 times 2 squared plus 30 equals -5 times 4 plus 30, -20 plus 30 is positive 10. Okay. That's interesting. So you might have expected it to go down by 5 meters each time, but it's not. It's accelerating as it's dropping by about 10 meters per second. So every second, the speed is increasing by 10 meters per second. That's one way to say that. Okay, how about 3 seconds? Let's see. Y equals -5 times 3 squared plus 30 equals -5 times 9 plus 30 equals -45 plus 30 equals -15. Okay, and now I'm saying we're at -15 meters, which obviously sounds weird. It means that somewhere in here we hit the ground, right? Before we got to 3 seconds. I'm not sure exactly how far, but somewhere in there we hit the ground. So the graph looks something like this. Here's our height axis, here's our time axis. 1, 2, 3, 4 seconds. 2, 1. And let's go by 5s. 5, 10, 15, 20, 25, 30. Okay, a lot of graphs just give you 2 numbers there so you can see the steps or relate the steps. I'll go ahead and draw some negative values here to get down to -15, since we have a point there with -15, just to see what the parabola looks like. Okay, the vertex is actually right here, and I didn't look at negative values of time because it seems a little weird, and so far as we know, negative values of time do not exist. So 125 is my next point, 210 right there, 3, -15. And I did it just so I could draw a nice little curve, this 3, -15 part. Okay. My graph's a little bit ugly. I'll draw a nice smooth line. Ooh, sorry about the squeaking. The axis of symmetry is actually right through the y-axis. We could continue this like that. That's what the parabola would look like. Now, mathematically, of course, the only part we can take is right here in the first quadrant. And somewhere about right there, that time is when we hit the ground. Whoa, excuse me. You probably saw that coming in video in slow motion. Zoom in on that. So one thing I wanted to say about the graph is this is not the trajectory of the object. The trajectory of the object was straight down. You just dropped it. Okay. Keep in mind that this x-axis here is now time. It is not a horizontal direction and a vertical direction. It's only a vertical direction in time. So that gets a little bit confusing sometimes with these equations. But stay tuned. Let me give you another one. Actually, I'm not going to stop this video because it's all related. Let me just go ahead and do it right now. Give you a different gravity equation. And then on the next video, I'll do another application of quadratic equations. Show you what the graph looks like. I think that's the first time I've sneezed on one of these YouTube videos. Why don't you edit it? Well, isn't it kind of fun to watch somebody sneeze? It's weird. All right. Plus, maybe you can zoom in real close and get a good distribution of the particles and do a statistical analysis. I don't know. Okay, here's another equation I was just sort of making up. How about y equals -5t squared plus 20t plus, we'll say, 2. How about that one? So which equation am I using? Which value of g? Well, automatically I'm using this value of g because remember that first term is just half of whatever there is there. Half of something to give 5 must be 10, so I'm talking about meters per second. So right away I can identify this equation as being a gravity equation in meters per second for the gravity. The height is in meters, the time is in seconds, and the velocity is in meters per second. So let's go ahead and evaluate a few things. First of all, what's the vertex of this guy? Whatever this is, some object that has an initial velocity of 20 meters per second, beginning at initial height of 2, and then, of course, accelerating towards the ground. Well, remember we can find the x value of the vertex, in this case the t value of the vertex, by taking -b over 2a. Negative, negative, I get a positive there. 20 divided by 10 essentially is 2, so the t value is at 2 seconds for the vertex. How about the y value, or height, in this context? Well, I can plug in my 2 seconds into the equation. Y equals -5 times 2 squared plus 20 times 2 plus 2, which gives me -5 times 4 plus 40 plus 2, -20 plus 40 plus 2 gets me to 22 meters at the vertex. Of course, the parabola is going down because the leading coefficient is negative, and we're starting out at a time of 2 seconds and a height of 22 meters for the maximum height. Okay. Let's go ahead and draw the graph. All right. And let's put 4 seconds on the clock. 1, 2, 4, just like we did last time. Time axis is right there. And I'm not quite sure on the vertical axis yet. Let's get a few values of time. Let's go around this vertex a little bit. So let me give myself some space here. T and Y. The vertex is at 2 seconds. I guess I should have thought about that before I did the other things here. 3, 4 seconds, I could say. A few values. Okay, so at 0, that's always a nice one. 0 is an easy thing to plug in. Y equals -5 times 0 squared plus 20. Wow, it's ugly. Times 0, you can fix it. Plus 2 equals 0, 0, 0, 2. All right. 2 zeros and then the 2. How about y at 1 second? -5 times 1 squared plus 20 times 1 plus 2 equals -5 times 1 plus, or let's just put all this together, 22. 22 minus 5 is 17. Okay. So I'm going to put 17 here. We already found the value at 2 seconds. That was 22 meters. And remember, this was the vertex. This was our central piece. And so we know that the axis of symmetry goes through the vertex. This must therefore be 17, and this must therefore be 2. So when's it going to hit the ground? Sometime after 4 seconds. Maybe we can just sort of guess, I don't know, from the graph. And what kind of scale do I want? Let's go by 5s. 5, 10, 15, 20, 25. And 5 down here for my y-axis. And I might put a few more hash marks in there to get the precision that I'm looking for. For example, the 22 Here's 20, so let's go 1, 2, 3, 4, and there's my 25. So here's 22. Match that up with 2. Oh, that's about right there. Okay. How about 0 for time, 2 for the height? 1, 2, 3, 4, 5. So about right here. Okay. And that makes perfect sense. Let's just say that this represents kicking a football or something like that. Maybe it's a punter. And this equation just represents the up and down motion of the ball. Started out at 2 meters, about 6 feet high. Okay, 117. There's 10, 15, 16, 17, 18, 19, 20. So about here. Okay. There's my axis of symmetry. So I can just go around that, say there must be a point. I guess I'll still use pink. 3, 2 there. Okay. And then this guy must be the same there. And I make a nice smooth curve, smooth as I can. And it looks like we hit the ground, of course. Right over here. It looks like just after 4 seconds at some point. Looks like before, I'd say 4.5 seconds, probably even before 4.25 seconds. You can get those exact values by solving the quadratic equation, setting y equal to 0. So once again, here's the graph in time, okay? The height versus time, not the vertical and horizontal trajectory. So stay tuned. I'll do 1 or 2 more applications in the next video.